Here we have a problem on finding domain and range of a composite function. So where f of x equals to natural logarithm of x and g of x equals to negative x. Okay, let me write the composite function f dot g. The formula to get composition of two functions f and g is f of g of x. Okay, to find the domain and range of a composite function, first we have to know what is the first function and what is the second function. So how do you have to know which one is first function and which one is second function? So let's consider the stuff we have over here, that is f of g of x. So for which function can we give input at first? So here, when I consider the composition of the two functions, the function g of x is clearly seen. So we can give input for g of x at first. Since we can give input for g of x at first, so this g of x, this function g, has to be considered as a first function. Let me write the stuff over here. And the other one, f, is a second function. Let me write it. Okay, now we got which one is first function and which one is second function. Okay, now let's understand what is domain. So to understand domain, let me consider one of the given two functions, so that is g of x equals to negative x. So here, how do we have to find domain for a function? So domain is a set of values of x for which g of x is defined. So for what values can we give for the x over here so that g of x is defined? We can give any real value for x over here. So for any real value of x, a function g of x is defined. So the domain of this function g of x is all real values. Okay, now to get the domain of a composite function, first we have to write the domain of the first function. In this case, it's g. Okay, now let me write the domain of the first function, that is domain of g of x. So just now we discussed the domain of the function g of x, that is all real numbers. Okay, now usually the domain of a composite function is the same as the domain of the first function, that is r in this case. Otherwise, the domain of the composite function must lie in the domain of the first function. Okay, so for that what we have to do is we have to find the result of the composition of two functions, that is f of g of x. Okay, now let me write f of, so we know the stuff for g of x, that is negative x, so we can plug in negative x for g of x over here. Then I'm getting, okay, already we know that f of x equals to natural logarithm of x. So if I have f of negative x, then I have to replace this x by negative x. In that case, I'm getting a natural logarithm of negative x. Now I got the result of the composition of two functions, that is the natural logarithm of negative x. Any logarithm is defined only for the positive value in the argument. So here this is the argument. So this is ln is natural logarithm. This natural logarithm is defined only for the positive value of the negative x we have over here. It is not defined even for the argument 0. So if I want this to be defined, the value we have in the argument, that is negative x, has to be positive, that is it has to be greater than 0. So this gives the domain of the result of the composite function. Okay, so here to get the domain we need the value of x, but here we have negative x. So I have to get up this negative sign. For that I have to multiply both sides of this inequality by negative 1. Let me multiply the right side by negative 1. So whenever I multiply both sides of an inequality by the same negative number, I have to flip the inequality sign. Already it's greater than, then it will become less than. So negative 1 times sin 2x is just x, less than negative 1 times 0 is 0. So this is the domain of the result of the composition of two functions f and g, that is ln of negative x. As I said earlier, the domain of a composite function is the same as the domain of the first function. In this case, it's r. Or the domain of a composite function must lie in the domain of the first function. That is, the domain of the composite function must be, can be a subset of the set of all real numbers over here. So how do you have to conclude? So here we got the domain of the result of the composite function, that is x less than 0. So here the domain of the first function is all real numbers. Okay, to decide the domain of the composite function, let me draw a number line which represents the domain. So here on the left side extreme we have negative infinity, on the right side extreme we have positive infinity. So here we find 0 in the domain of the result of the composite function. Let me mark the 0 here. Okay, first let me draw the domain of the result of the composite function, that is x less than 0. So x less than 0, here 0 is not included. So since 0 is not included, we have to take an empty circle at 0. And since it's x less than 0 means, like in interval notation we have negative, negative infinity less than 0. So we have to start from 0, we have to move to the left up to the left side extreme negative infinity. So this is a graph of the domain of the result of the composite function ln of negative x. Okay, now let me draw the domain of the first function g of x, that is all real numbers. Since the domain of the first function g of x is all real numbers, so I have to cover the entire interval from negative infinity to positive infinity. Now, let's find the common region of these two graphs. So the common region of these two graphs will give the domain of the composite function f dot g. Okay, what's the common region over here? So this is a common region of the two graphs. This common region gives the domain of the composite function. So the interval notation of this common region is going to be negative infinity comma 0. So this is the domain of the given composite function f dot g. Okay, now we have finished defining domain of the given composite function. Okay, let me erase some stuff and continue with the range. Okay, now let's see how to find the range of the given composite function f dot g. Okay, before that, first let's understand what is range. To understand range, let's consider one of the given two functions, that is f of x equals to ln x. So the range is the values of f of x. Actually, domain is the values of x for which the given function is defined, and range is the set of values of the function f of x or ln x, because ln x is the stuff which is equal to f of x. Okay, so how do you have to find the values we have for f of x or for this ln x? So like already we know that like argument of any logarithm will always be a positive value, it cannot be even 0. So like when I take like x is greater than 0, so when I take, since x is greater than 0, like we can mark like this, we can start plugging in a value which is greater than 0, means like we can take a very small value that is in decimal form, like even you can take x is equal to 0.0001, something like that. Okay, because this is also value which is greater than 0. When I plug in this kind of very small value for x over here in the argument of natural logarithm, so its value will be a very large negative value. So like when x approaches 0, actually x is not equal to 0 because the argument x always has to be greater than 0. For example, I'm saying when x approaches 0, this ln x will approach a very large negative value, that's called negative infinity. So the lowest extreme of this ln x is negative infinity. Okay, when I take a very large positive value for x over here, then the value of ln x also will be a very large positive value. So the right side extreme is positive infinity. So the value of this ln x or this function f of x is any value between negative infinity to positive infinity. So this is the range of the function f of x. Okay, now to get the range of a composite function, first I have to I have to get the range of the second function. In this case, it is f. Okay, now let me get the range of the second function, that is range of f of x is, just now we discussed the range of f of x, that is ln x, that is negative infinity comma positive infinity. So let me write over here. Usually the range of a composite function is the same as the range of the second function. Otherwise, the range of the composite function can lie inside the range of the second function. That means the range of the composite function can be the subset of this interval. Okay, now what we can do is we can find the range of the result of the composite function, that is ln of negative x. Already we discussed the domain of this result of the composite function, that is ln of negative x, that is x less than 0. That is x over here can take only negative values. Okay, so let's consider a value for x which is very close to 0, and also it has to be on the left side of 0. Then we can consider x equals to negative 0.001. So this is a value which is very close to 0 on the left side of 0. So when I plug in for x over here, what will happen? Let's see. ln of so we have negative sign of it, and the value of x is also negative. So negative times negative will become positive, then we get 0.001. Okay, here we have a very small value. So whenever natural logarithm or any logarithm takes a very small value, that is less than 1 in the argument, the overall value of the logarithm will be a very large negative value. So when x takes a value which is very close to the 0 in domain, so we get a very large negative value for the result of the composite function. Okay, what if x takes a value which is far away from 0? That is a very large negative value, for example, negative 1000. So let me see. So ln of, already we have negative sign over here. The value of x is negative 1000. Negative times it will become positive. I'm getting ln 1000. So whenever we get a value over here, it's a large positive. The overall value of this natural logarithm also will be a very large positive value. So clearly the range of this ln of negative x is going to be negative infinity to positive infinity. That is in the domain x less than 0, when x takes a value which is very close to 0, or when x approaches 0, then the value of this natural logarithm of negative x approaches negative infinity, a very large negative value. So when x approaches a very large negative value that is far away from 0 on the left side extreme, so it will become a very large positive value. In that case, this overall natural logarithm will approach positive infinity. So the range of this the result of this composite function is negative infinity to positive infinity. Already we got the range of the second function, that is negative infinity to positive infinity. So now how do you have to conclude the range of the composite function? So for that, let me draw a number line which represents the range. So here on the right side extreme we have positive infinity, here on the left side extreme we have a negative infinity. Okay, now what I'm going to do is I'm going to sketch the graph for the range of the result of composite function, that is negative infinity to positive infinity. Since the range of the result of the composite function is negative infinity to positive infinity, so we have to cover the entire interval negative infinity to positive infinity. So this is a graph for the range of the result of the composite function ln of negative x. Now let me graph the range of the second function f of x, that is negative infinity to positive infinity. So this one also will cover the entire interval from negative infinity to positive infinity. So what is the common region for these two graphs? So the common region is the entire interval from from negative infinity to positive infinity. So the common region of these two graphs will give the range of the composite function f dot g. So the common region of these two graphs gives the interval negative infinity to positive infinity. So therefore, the range of the composite function f dot g is the common region over here of the two graphs, that is negative infinity to positive infinity. Let me write over here. Otherwise, it can also be written as negative infinity less than y less than positive infinity. So usually we use the variable y to represent range.